This is a joint work with Omer Tamuz from Computation. And as we know, and there is broad experimental evidence that individual choice behavior has a certain random component. And this randomness can have many different origins. So for example, it may come from random taste shocks, or it can be shaped by cognitive or information processing costs. It may come from some noise in the underlying neurological decision process, or maybe people just like to randomize, and so they randomize deliberately. So in this paper, we asked the following question: how should one model this inherent stochasticity in individual choice behavior? So we look at the behavior of a single individual across many possible decisions, and we do not contribute to this debate on the origin of randomness. We are completely agnostic, and we take axiomatic approach. So this approach has two features. First of all, we will impose a relatively weak requirements on the behavior, but we will compensate for this weakness by assuming that they apply over a broad range of decisions. And the key requirement will be what we call decomposability axiom, that captures the idea that unrelated decisions should not affect each other. Okay, so let's jump right to the model. A single decision instance is modeled as a menu. This menu is a pair, A-O, where A is a finite set of available actions, and O is a map that assigns a certain numerical outcome to each action in our menu. And it's convenient to think of these outcomes as some monetary rewards or costs associated with this. So you can think of a menu representing choice of morning coffee. Say you have two options, two actions S and T with outcomes 1 and 2, or maybe there is a menu representing choice between job offers A, B, and C with outcomes 3, 17, and 17. So the idea is that we can model lots of things within menus. The behavior of an individual across all these universal menus is represented by a stochastic choice rule. So a stochastic choice rule phi, it takes a menu as an input and outputs a probability distribution over the set of actions. So we will denote this distribution by phi AO. And by phi AO of A, we will denote the weight assigned to the action A. And we interpret this as a predicted probability that our agent will take action A if she faces this menu AO. So we can think of phi as a certain theory predicting or describing our individual's behavior or in every possible menu. So just to give you some examples, you can think of the following stochastic choice rules. A rule for each menu outputs the uniform distribution over all actions that have maximal outcomes. Slightly perturbing this example, we obtain the popular class of additive random utility models. So now, in every menu, we perturb every outcome by some IID shocks coming from some fixed continuous shock distribution. And then the probability that the action A is chosen is just the probability that this action has the highest perturbed outcome. Another arguably most popular example is the multinomial logit rule. And so phi is multinomial logit if there is a constant beta, which we will assume to be fixed across all possible menus. such that phi is given by this expression, and multinomial logit is actually a particular case of this additive random utility family that corresponds to noise distribution, to Gumbel noise distribution. Okay, so what are the assumptions that we want to impose on stochastic choice rules? First of all, it's a neutrality. Neutrality says that whenever in a menu we have two actions with the same outcomes, these actions must be assigned with the same way, the same probability. And the idea behind this property is that we want our rule to be driven by the profile of outcomes rather than actions names, actions labels. To formulate our main axiom, decomposability, I first need to define the operation of combining two menus. So suppose we have two menus, A101 and A202, and we define a product menu, AO. This is a menu where the set of actions is just the Cartesian product, and the outcome assigned to a pair of actions, and actions from the first menu and actions from the second, is just the sum of outcomes. So just to give you an example, consider these familiar menus of choosing coffee and choosing job offers. Their product will correspond to a menu where you simultaneously choose coffee and a job offer. And the fact that the outcome is defined in this additive way captures the idea that there are no complementarities between these two dimensions. So the choice of action in the first menu does not affect the marginal outcome in the second menu, and vice versa. So you can think of this operation of taking a product as a way to combine menus so that you create no complementarities across outcomes. Okay. We say that a rule phi is decomposable if for any product menu, phi outputs a product distribution. This is a product distribution of the prediction for the first menu and prediction for the second menu. So if we think about our coffee and job offers examples, this means that, first of all, the choice prediction for coffee is independent for the prediction for job offers. And second, each of these two predictions are exactly the same as if they were made in isolation. So you're going to think of decomposability as a certain consistency requirement on the behavior of a choice rule across menus. The interpretation that I particularly like would be the following. So imagine that we run a lab experiment and we are interested in agents' behavior only in the first menu, A101. And unavoidably, we need to assume that what we observe in this lab experiment must be independent by what our subjects do outside of the lab. It must be unrelated, unaffected by choice problems that they face in the background, and this is what decomposability gives you. Any questions about the model or the axioms? Okay. So here is the question we asked. What are the rules that satisfy neutrality and decomposability? And it's easy to see that multinomial logit does the job. And so the question is, what else? And the answer is that essentially that's it. So our first main theorem says that if you have a rule that satisfies neutrality, decomposability, and an additional technical assumption of contiguity, which can be replaced by measurability, then phi is necessarily multinomial logic. So just to reiterate, it means that there exists a constant universal, the same for all menus, so that for each menu, our rule is given by this formula. So in other words, our axioms, they pin down a one parametric family of rules. And in particular, if you observe the prediction on a single non-trivial menu, it determines the prediction for all other menus. One thing that I want to stress is that we have not assumed that our decision makers are rational, that they maximize a certain objective. We only assume that their behavior satisfies these axioms. And it turns out that it implies that they behave as if they are stochastic utility maximizers. So somehow magically we get rationality out of these axioms. Questions?
Is there any intuition? Is there something about Gumbel distribution that we could like? Why not just general randomity?
So the Gumbel distribution has an exponent in its definition, right? And the logic rule has an exponent. So the exponent has a nice property that the exponent of a sum is the product of the exponents. I guess that's rough intuition. That's why Gumbel is shows up and why we get a logic. But actually, my plan is to give you some, give you a sketch of the proof. So for this baseline result is pretty easy. Mm-hmm.
How technical is continuity? It seems to rule out a lot of stuff.
It rules out two reasonable rules and a lot of crazy rules.
Sorry, it rules out what? Sorry?
It rules out two reasonable rules and lots of crazy rules. So reasonable rules are the following. The one that I actually mentioned, the rule that outputs the uniform distribution on the highest outcome actions is discontinuous. The rule that picks up the uniform distribution on the least that have least outcomes is discontinuous. So these are two reasonable rules that we rule out, and other rules that are ruled out, they are discontinuous everywhere and non-measurable. So in a sense, you need the axiom of choice to show that such rules exist. So this is why continuity is.
So if you replace continuity with measurability, you get this and the two rules that you mentioned?
We get this plus the two rules.
Okay, thank you.
Thanks.
That's why I couldn't answer so quickly.
Okay, so a quick sketch of the proof. So suppose we're given a rule phi that satisfies neutrality, decomposability, and continuity. And for simplicity, let's also assume that it puts positive weight on any action in any menu. What we need to show is that phi is given by this formula, but it is easier to show the equivalent identity. So for any two actions, the logarithm of the ratio of probabilities must be a linear function of the difference in outcomes. And I want to show this for binary menus. So let's look at a menu with actions A1 and A2 and outcomes 0 and x. And denote by f of x the probability that is assigned to the second action. So I want to prove that the following identity holds. So how we do that? We consider a product of three binary menus with outcomes 0 and x, 0 and y, and 0 and x plus y. And what is nice about this product is that it has two actions with outcomes x plus y. So you can get x plus y by choosing A1 and A1 in the first two menus and A2 in the last one, or you can choose A2 and A2 in the first two menus and A1 in the last. By decomposability, the corresponding probabilities assigned to these triplets admit the following representation through our function f. And by neutrality, these two expressions must be equal, and so we get the following functional equation on f. And if we define the following function u, then it satisfies the Cauchy equation. And it is known that any continuous solution or even any measurable solution to this equation is linear. And that's it. And of course, I will skip the extension to arbitrary limits. In the remaining 1 minute, I want to briefly mention some of possible generalizations of this rule. First of all, the conclusions are robust. If you consider rules that approximately satisfy axioms, they will be close to logic. Second, so far we focused on actions having deterministic numerical outcomes. In the paper, we discussed stochastic outcomes, payoff streams, and even some abstract outcome spaces. And also, it turns out that this approach generalizes to multiplayer games. This is something that we do in an ongoing project with Omer and two brilliant Caltech students, Perkan Son and Beth Winselberg. In case you go to Stony Brook, Perkan will present this paper there. So what we show is the following. So if you look at n-player normal form games, and you look at solution concept to each game assigns a certain non-empty set of mixed strategies. You can define a version of decomposability, and you can define a version of monotonicity, which roughly speaking says that agents assign higher weight on those actions that generate first order stochastically dominating rewards. And it turns out that as a result, we obtained Nash equilibrium, logic theory, and some new solution concepts for agents with non-trivial risk attitudes. And that's it. Thank you.